Hi everybody. Today we will continue the electrical potential chapter 3. Okay, so the potential, the unit of the potential energy is joules, but the unit of potential is volts. Okay, so always keep this in mind. There is a distinction between the two. Now let's assume that one charge is moving from point A to B, and maybe there are some electric fields like this. Okay, electric field distribution, not necessarily constant. So if we assume that this is dl vector, this one, and this is electric field vector, and the angle between them is alpha, then we know that the work done on Q0 by electric field is given by, from A to B, is given by simply, okay, delta K, which is equal to minus delta U, and it's equal to also the force times the distance. Okay, force vector times the distance vector. So this is a dot product, and as you see, this dot product is F dl times cosine alpha. Okay, so we have to consider also the angle between the two, and also we know that the force due to the electric field is just Q0 times E. Okay, so if the object, or if the charge is moving from point A to B, somebody is doing the work, and in this case the electric field is doing the work. And if you put the electric field here, okay, then we can say that WAB, which is equal to minus delta U, it's also equal to E over E times Q0, because Q0 E was F times dl. So if you divide both sides by Q0, you get WAB over Q0 or minus delta U over Q0, which will be equal to E dot dl. Okay, and we call this as delta V. Okay, or delta V with a minus sign. Okay, delta V with a minus sign, because this is defined as delta V. Okay, so now delta means that, always don't forget, after minus initial. So if we are talking about delta U, it's UB minus UA, because UB is the potential at point B, UA is the potential at point A. So whenever you have delta, it's always the final minus initial. The final, in this case, B, but the initial is A, because the object is moving from left to right. Okay, from A to B. That's why when you put this as UB minus UA, then you can write this as VA minus VB using this minus sign. So this is equal to E dot dl. Okay, so this is the expression which shows that if there is a potential difference, then this may be due to the electric field times the distance, okay? Because the charge is probably moving from one potential to another potential. If the two potentials are the same, the charge is not able to move from this point to that point, obviously. So in this case, we see that the potential difference, okay, is given by that. But don't forget, this is not delta V, but minus delta V. Always keep this in mind. From here, delta V is also is equal to delta U over Q0. Okay, don't forget the unit of U is joules, but the unit of V is volts. So how can we get the expressions for potential and potential energy? So let's assume a point charge, okay, which produces electric field lines in three-dimensional space, okay, plus Q. In this case, we would like to put some kind of test charge here, Q0, okay, and then allow it to move in the direction with the electric field, so that it will move in this direction if it is put R away from this Q, okay? So now dl is this, and this is our test charge, which is moving exactly in the same direction with the electric field, which is created by Q. By the way, we assume that this is fixed, because if one charge is moving and the other is also moving, the electric field also changes. Okay, not according to this distance, but also the distance. Okay, that will change due to the motion of this charge. So basically, and the direction of the electric field will be changing. So whenever we do this kind of analysis, we assume one of the charges is fixed. Okay, in this case, Q0 is moving. It's very natural, because if it is plus and plus pushes plus, and this moves in the direction with the electric field, and the work done by the electric field should be positive. So for this one, work done on Q0 by electric field is positive, because it's very natural way. But if you have another charge, but you push it this way, which is not easy, because now plus pushes plus, and as you see, although the electric field is in direction, dl is in opposite direction, so that there is 180 degrees, and cosine of 180 degrees gives you -1. It means that the work done is negative. So there will be a minus sign due to this dot product here, dot product. So in this case, work done on Q0 by E field is negative, because somebody else does the work. Somebody must do the work. If electric field is not doing the work, then somebody else is doing the work. Okay, maybe my finger is doing the work by pushing this towards this charge. Okay, so in this case, in natural case, okay, let's see what the force between the two when we have this case here. The force between the two charges is the Coulomb force that you remember, Q0, because the charges are Q and Q0, and the distance between them is R squared. Okay, so now when we have this force here, then we can just insert this delta U with a minus sign, which is equal to, I'm using this equation, by the way, integral sign, okay, K Q0 over R squared dr. Okay, now don't forget, the force as a vector is written as K Q0 over R squared times R unit vector, okay, because it's radial outward, and dl vector that you are using is here is dr times R unit vector. When you dot product, R unit vector dot R unit vector gives you 1, and we have this expression. So, and the good thing about these two vectors is that they are both in the same direction. We are considering this case, by the way. Okay, so all we have to do is just integrate this, okay, from A to B. Suppose this is point A and this is point B. The charge is moving from A to B in the same direction. Okay, so delta U is just by using this UA minus UB, okay, because delta U is UB minus UA, but if you use minus sign, then it will be written as UA minus UB is equal to K times Q0, these are constants, 1 over R squared times dr from A to B. So the integration of 1 over R squared is just minus 1 over R, okay? So K Q0, okay, minus 1 over R, and the limits are A and B, okay? So from this, you can write this as, okay, use the minus sign, but by taking this minus sign and changing it to positive means that you're just changing the limits. So instead of putting these limits like that, we can put the limits like A and B here, but with this positive sign. So K Q0, okay, 1 over RA, okay, minus 1 over RB. And left hand side is UA minus UB. As you see, this is just the difference between the two terms, and this is also difference between the two terms. Then these terms should be identical. So from this, I can see that UA is equal to KQ0 over RA, but UB is the same with RB on the denominator. So from this expression, we can see that the result is that the potential energy is given by KQ0 divided by R. Okay, so the force was given by this, where R square was on the denominator, but here we have R on the denominator, so it's called the potential energy. As you see, in order to talk about the potential energy, you need two charges, or more than two charges, maybe a few charges, as we will see later. Okay, but what about the potential? If you divide this U by this Q0, because Q0 was the test charge, then U over Q0 will give you V, and it is equal to KQ over R. As you see, this is called potential. But this is potential energy. So what is the difference between the potential and potential energy? As you see, the potential is due to whatever is producing the electric field, okay? Its charge is here. There is no Q0 there. So this potential is automatically created by this charge, okay, when it's just fixed in a space. Not necessarily from a point charge, of course. It can be surface charge or line charge density or ring charge density, as we have solved earlier. So any charge that really is sitting in the space, even in moving, will produce a potential. And the unit is volts, so it will produce a voltage. Any charge will produce a voltage in the space. But in order to talk about potential energy, you need to bring another charge to it so that you can talk about the potential energy between them. So unless you bring other charges next to the charge which produces electric field, you cannot talk about the potential energy. You can only talk about potential. It has a potential to create the potential energy if there is another charge involved. Okay, so this is the distinction between the potential and potential energy. Okay, so potential is the potential energy per unit charge. Per unit charge. Okay, so let's go on. Let's have a few charges like this in space, like that. Okay, three charges, Q1, Q2, and Q3. Okay, now if you can measure the distances between them, okay, you don't need any vector business, right? Remember, for the electric field, we had X and Y components, but now to calculate the potential energy, all you need is to know the distances between the two. So the distance between second and the third charge is R2, 3, and the distance from between 1 and 3 is R1, 3, and the distance is R1, 2. So that if you know these things, the potential energy is given as the sum, okay, K of course will be there, I and J, Qi, Qj divided by Rij. Okay, this is an expression. It shows you that you have to get all the combinations. So this is now K times Q1, Q3 over R1, 3 plus K Q1, Q2 over R1, 2 plus K now 2 and 3. So as you see, you consider all the charges against each other, okay, R2, 3. So when you insert these values, you can get the potential and this potential energy, and this potential energy can be plus or minus, okay, depending on the charges. So they can be positive or negative charges. Some of these terms may be negative, some of them positive, but when you add them up, you can get any kind of sign, okay? So the potential energy can be negative or positive, okay? So now, what about the potential? If a few charges are sitting, then there is a possibility that they create some kind of potential. So for instance, these charges, these three charges, if they are fixed, they will create a potential here, but all you need then is to measure the distances okay, to these charges. If you can measure the distances to these charges, add the potentials differently, okay, and then it's just a scalar summation, then you can find the potential. So if this is R3 and it is R1 and this is R2, which is the distance from these charges, then the potential at point P, okay, at P is simply given as K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3. As you see, you don't need any direction information, any vector combination, nothing, because potential and potential energy are scalar quantities, okay? The unit of potential is, again, volts, don't forget, okay? And the unit of the potential energy is just joules. Always keep this in mind. So in order to calculate the potential and potential energy, all you need is just distances and also the information about the charges, okay? Now, let's do some experiments. Suppose that we have now, we have this x direction, and at x equals 0, we put a charge which is minus E, okay? So Q1 is equal to minus E. It means it's an electron. So at x equals A, we put Q2, but it's plus E, it's a positron, okay? Of course, you do this experiment in vacuum. Let's draw the vacuum, okay, like that. So from very far away places, you bring another charge, Q3, okay, which is also another positron, here at x equals 2A. So it's coming from very far away, okay? So this is initial, and this is final for this positron. It's moving, okay? It is being brought from this point to that point. Okay, nice. So if this positron is moving from infinity or very far distances to this point, the electric field that is created by these two charges, which are fixed, assume that these are fixed, by the way. This is fixed, also this is fixed. And of course, this creates electric field. And if you look at the electric field that this positive charge produces, is going to be this way, to the right. But for this one, it's going to be to the left, but it will be smaller in size because the distance is greater. So we expect a net electric field, which is in positive x direction at this point, okay, due to these two charges. In this case, as you are moving opposite to the electric field, just like this case, okay, you are moving opposite. So the work done by the electric field is to be negative. So we expect the work done to be negative. So what is the work done by the electric field created by these two charges on this Q3? W on Q3 by Q1 and Q2. What is that? It's equal to minus delta U, which is U initial minus U final, okay, which is equal to, okay, which is equal to integral F dot dl. Okay. Now we assume that when this charge positron is so far away from this combination, okay, the potential is 0. So this is, as you see, this is 0. Initial potential is assumed to be 0, and now we have just minus. So W on Q3 happens to be negative. So it means that the electric field that is produced by the combination of these two charges is not doing the work, but somebody else is doing the work because we have to push it. And now, as you see, this plus pushes plus, and you're just forcing it. Okay, so it's very natural. So knowing that the work done is negative, we can find out the total potential energy. Okay, so the total potential energy, okay, is for this case is given by just three terms, because you have to consider all the couples together. So the potential energy of the system is equal to, okay, Q1, Q2 with K, of course, divided by R12 plus K, Q1, Q2 over So it's K with minus K E square divided by R12. So the distance between the first and the second charge is just A. If you just look at these three terms, the result simply is K times E square over 2A with a minus sign. With a minus sign. As you see, the potential turned out to be negative. The potential turned out to be negative. So, and also the work done is negative because somebody else is doing the work by putting this charge nearer to these two charges. Okay. So, potential is the potential energy per unit charge. So, if the potential energy is obtained by this expression, then the potential can also be obtained by K I J, okay, K, okay, I Q I over Ri, okay. There is only one sum here, but two sums there. Okay, so basically this is it. So now we have this expression, don't forget, VA minus VB. If the object is moving from A to B, it is equal to, okay, just minus, okay, E dot dr. Okay, E dot dr, the minus sign. So this is the equation to be used. I would like to solve now an example where there are two charges, okay, sitting side by side and producing some kind of potential at a point, at several points, and get these potentials due to these two charges. Okay, now, example. So on this x-axis, we have Q1 sitting here, Q2 here, okay? And just between them, okay, just the center line passing from them, there is a point C, there is a point C here, and the distance is given as 13 centimeters here, and the distance again here is the same, 13 centimeters. So they have the same distance, but this Q1 is plus 12 nanocoulomb, and this is minus 12 nanocoulomb. Okay? And also, we would like to find what is the potential at point C. And what is the potential at this point A, where this is 6 centimeters, and this is 4 centimeters. Okay, so we would like to find out what is the potential at point A. So here, as you see, the potential due to this charge, which is plus, and minus signs are exactly the same because the distances are the same, and the charges are also the same. So that the potential here is going to be 0 because they will cancel each other. So VC is simply equal to 0. Okay. Because one potential is positive, the other potential is negative, and they totally cancel each other. But how about the case here? Okay, so the potential at point A is just K times 12 nanocoulomb, okay, divided by the distance, but it's 6.06 meters, okay, plus 12 nanocoulomb, but with a minus sign. So put the minus sign here, minus K, again 12 nanocoulomb divided by the distance, which is 4 centimeters, 0.04. Okay. So if you just put these values, 9 times 10 is 12 is 12 times 10 to the minus 9 divided by 0.06, okay, minus 9 times 10 to the 9 times 12 times 10 to the minus 9 again. So they cancel each other, as you see. This 9 and minus 9 cancel each other, and then 0.04. So the result from here is going to be simply, okay, minus 900 volts. So here the voltage is going to be minus 900 volts. Okay. So now, as you see, each of these charges, when they are fixed, they produce their own potentials at any point, and they are given by these two expressions. And to get the total potential, you have to just add them up. Okay. So now let's do this point charge problem, and let's show that this equation that we have derived is correct. Okay. So now we have now this expression that we are using. Let me write the expression. Okay, VA minus VB will be equal to minus E dot DL, okay, from A to B. So this is the expression we are using, or just delta V is equal to EDL. Same thing. So don't forget, this delta V and VA minus VB are inverses of each other. So this is, okay, this is VB minus VA, but on the left-hand side, we write VA minus VB. Now, let's look what happens when we have point test charge. If we have a point test charge which produces electric field in three-dimensional space like that, okay, we move now from one point to another point. Okay, this is point A, and this is point B. So we are moving in this direction. And DL vector is written as dr r unit vector, and electric field also is written as a vector E times r unit vector. Okay. So E dot DL is just EDR. So this gives you just EDR, because both of the vectors are parallel to each other, so that their dot product gives you simply this result. So now, if we know the electric field due to this test charge, which is fixed, by the way, okay, then we can just integrate to get the potential. So now, assume that B is like infinity, okay? So B is so far away. In this case, we expect that potential to be zero at infinitely far away from the charge. Don't forget, there is only one kind of charge here. There is no test charge, nothing. We're just considering these 2 points, point A and point B, but B being very far away, so that the potential is zero. So the second term is zero, so VA, okay, minus 0 will be equal to, with minus sign, from A to B, but A is this written here, and then minus sign there. Okay. Okay. Now, VA minus infinity. Okay, this is correct. And now E dot dr. But now electric field is just K Q over R squared times dr, and put it to the other side, so that VA will be equal to, okay, K Q 1 over R, okay, 1 over R with a minus sign, okay, from A to infinity. But if we use the infinity, 1 over infinity will give you 0, but the lower limit will give you 1 over r, so it will be just k q over r a, which shows that the potential is just given by k q over r. Okay, if you are away from this point, okay, this fixed charge. So the potential is given by this expression. Okay. All right. So now we did this experiment, this example. Now let's do another example. Okay, another example with some other shapes. For instance, we consider now a shell, and then the charges are distributed on the shell. Doesn't matter if it is conducting or non-conducting. As far as it's a shell, we know that inside electric field is totally zero. But outside, we found that at a distance r, which is greater than r0, which is the radius of the sphere, okay, spherical shell. Okay, at this distance, we know the electric field is given by k q over r square if the total charge on the surface is given by q. Okay, and the direction is here, we know. Okay, it's radial outward, just like the point charge, as if this field lines are coming from the point charge in the middle. But in this case, it's just all the charges are now on the surface. But inside, we know that its electric field is totally zero, and it acts like a Faraday's cage. So now we would like to draw this graph, electric field as a function of r, which is here until r0, it's totally zero, and then after that point, it just drops like that. And it's the behavior like 1 over r squared. Now, what about the potential? How can we find the potential? Away from, from this shape, the potential at this point is just k q over r. Okay, just because of the reason that I have told you earlier. This is the expression that we have derived from the point charge, but it gives you exactly the same thing. But inside, what is that? So this is correct when r is greater than or equal to r0. Okay, so at r0, then the potential is just simply k q over r0. Okay, this is the potential. Now, what about the potential inside? Okay, to derive the potential inside, we have to use VA minus VB, which is equal to E dot dl, but this is zero. Okay, why? Because inside, this is inside, by the way. Inside, electric field is zero, totally. So this integration is totally zero, but now VA and VB can be taken as this point A and this point B, which is at any distance, which is r. R is smaller than r0. So if we consider A as surface potential and B as regular potential at R or point B, which is going to be equal to zero because there is no electric field here. In this case, V surface will be equal to VR. So it means that all the points inside this, all the points will be equal potential, at equal potential. So whatever the potential here, maybe 200 volts. Inside, you can measure 200 volts everywhere the same. So potential will be constant, as you see, inside. So now if you draw the potential as a function of R, it will be constant, but will drop like 1 over R. Okay? And the constant being, okay, this K Q over R0. This is the constant potential. This Faraday's cage. Now, suppose that we measure the potential at this point, or at this point, or at this point, or at this point. As far as you are following the figure, you see that it will give you the same potential. So we can draw these kind of lines, and these are called equipotential lines. Okay, equipotential lines. So it means that at these lines, any point, the potential is the same. Same potential. As far as you are along this line. But if you go from one line to another, then the potential changes. You go to another equipotential line and the potential changes. Of course, the potential will reduce if you go away from the charge distribution. If it is a point charge, again the same scenario, okay? Again the same scenario. The equipotential lines will be totally spherical, okay? It's like the spherical shell. But now there is a really interesting property. If this is electric field lines, okay, and these are the equipotential lines, the angle between the two is always 90 degrees. So they are perpendicular to each other, as you see, at any point in space, at any point. So equipotential lines and electric field lines will be totally perpendicular to each other. E and equipotential lines are, okay, perpendicular to each other. We will see that if we have other kind of shapes like this, like a straight charge distribution, okay, the equipotential lines will be straight, okay, equipotential lines will be like that, okay. So these are equipotential lines, and the electric field lines will be always perpendicular to them, obviously. These are electric field lines and these are equipotential lines, and they are perpendicular to each other. Now, suppose that we have like funny looking shape, okay? So one flat and one flat surface and one point surface, okay? This is, say this is plus and this is minus Q, let's say. In this case, say total charge is Q. The electric field lines that are coming just outside this line, okay, charge that distribution will be like that. But as they move in space, they will be able to catch these lines, okay? Because this charge has electric field lines which are coming towards itself. So this catches that, and this catches that, and probably this one catches that one, and then this one catches this one. And as you see, there will be some curvature in the electric field lines. As soon as you put this charge, okay, here, these two charge distributions will be able to feel each other, okay? Will be able to feel each other, and there will be some kind of curvatures. But now, the interesting thing happens. When you are so close to this flat charge distribution, the equipotential lines are flat, but when you are getting away, there starts some kind of curvature like that, okay? Now, what happens is that when you get closer and closer to this thing, to this point charge, it becomes totally spherical in shape. So these are equipotential line, okay? And these are the electric field lines. Guess what? They are all perpendicular to each other at any point, at any place, okay, like that. They are all perpendicular to each other. So now flat equipotential lines are now is changing to a curved one. Suppose that this is like 100 volts, okay, and say that this is 0 volts or just minus 100 volts, okay, 100 volt minus 100 volts. So maybe this is 90 volts, maybe this is like 70, maybe 50, 30, 0, okay, and then 50, 70 with minus signs and minus 100 here, okay, very, very near. As you see, the potential, equipotential lines will have some curvature as they get closer to the point charge. If there are 2 point charges, okay, like this, plus and minus, say their charges are equal, the electric field lines, you know, are, okay, drawn like that, okay. As you see, there will be some curvature due to these 2 point charges. But now, what about the equipotential lines? Equipotential lines will be almost spherical when they are near these charges, but when they are just the midpoint will have this kind of flat distribution, okay? Because this is the only way that you can draw perpendicular lines to these electric field lines, okay? Because they are all towards right, okay, at this point, so that this must be flat. But on the right side, this flatness changes, and then we have these kind of curvatures, and okay, these are going to be just the equipotential lines which have some curvatures like that. Okay, so we learned the equipotential lines and also how these charges are connected to each other and so on. So next time we will solve a few more examples, and also I will do some experiments and make this problem easier to